Welcome to the Quantum Feedback Loop podcast. I'm your host, James Myers, and I also publish the Quantum Record, which features the latest in science and technology. If, like me, you're not a physicist, chances are you might still have heard about the second law of thermodynamics, which is a bedrock principle in physics. It's the law that says the arrow of time only goes one way from past to future. But is there something more fundamental? It's a question raised by our guest, Twesh Upadhyaha. Twesh is a PhD candidate in theoretical physics at the University of Maryland, where he's a researcher in Professor Nicole Younger-Halpern's Quantum Steampunk Laboratory. Thermodynamics is the study of changes in energy's various forms of heat and work, and its effects on the physical properties of matter. Twesh gives us an overview of the past 2 centuries of the science of thermodynamics, and leads us from its study at the classical level of what we can see with our eyes to the latest discoveries at the quantum level. Join Twesh in exploring the frontiers of thermodynamics as he explains the hidden world of energy at the tiniest level of atoms and molecules, its fascinating connection with information theory, the discovery of what he calls an entire family of constraints within the second law of thermodynamics at the quantum level, and the open question, what does entropy even mean at the quantum level? Here's my discussion with Twesh. I hope you enjoy learning about the research of the Quantum Steampunk Laboratory and the operation of energy at its most fundamental level as much as I did. Well, welcome, Twesh, to the Quantum Feedback Loop podcast. I'm really interested in hearing about this relatively new area of quantum thermodynamics.
Yeah, thanks so much, James, for having me. It's a pleasure to be here.
So maybe you could start by telling a bit about your background and your current research and studies. What do they focus on?
Yeah, so I kind of started off an undergraduate studying engineering physics at the University of Toronto. And I then went on to sort of specialize a bit more in the side of quantum information, quantum mechanics, with a master's at the University of Waterloo and the Institute for Quantum Computing. And now I'm at the University of Maryland in the group of Professor Nicole Younger-Halpern, studying quantum thermodynamics.
What kind of focus is your studies currently on in terms of what kind of work you're doing in the lab?
So one thing we've been thinking about a lot in the last couple of years with my collaborators is about how non-commutation, which is a very quantum phenomenon that I'm sure we'll get into later in the podcast, can really upend a lot of expectations in what normally happens in classical thermodynamics. So we've been looking at what are these sorts of new effects that can arise. And one thing that we focused on a lot is how it can change the very definition of entropy production. And, sort of preview entropy is another thing that I'm sure we'll get into details of shortly.
Yeah, those concepts we'll definitely look at. So maybe to start with, if you can just give us an outline of the history of thermodynamics, what it is, who the main players are, what the main ideas are in classical thermodynamics.
Yeah, so I think, some thermodynamic ideas or thermodynamic adjacent ideas have been floating around for a long time, but in the sort of modern conception of what we consider thermodynamics, it was Carnot who was really the first to start to put these pieces together. And it's actually interesting, his work came out 1824. This is the 200th year anniversary of his result. And he was really motivated in a very practical sense by the efficiency of engines. So in that era, these steam engines had just started to take force, and he was wondering, well, I have a steam engine and it's only converting some of the energy in this hot coal into work. Is that a reflection of somehow imperfect engineering, or are there more fundamental limits that nature imposes on what we can possibly do with this heat source? Then, a little bit later, Clausius came along and really formulated thermodynamics and was kind of one of the first to put down these first and second laws in the way we understand them today. And he was also thinking in terms of, well, what is this heat that we talk about? We see heat, where does it really come from? Well, he's kind of started to think about, well, maybe this heat is like the kinetic energy of these little molecules and make up a substance. And that kind of starts to reflect this shift of thinking from just thermodynamics, which is sort of this effective theory for heat and work, even if we don't know exactly what's going on under the hood, to people thinking about, well, how could we derive some of these results from scratch? How can we understand the underlying gas, liquid, whatever's going on? And that really is kind of a shift from thermodynamics to more statistical mechanics, where we're thinking about the statistics of ensembles of tons and tons of particles. So, like 10 to the 23 particles. And here Maxwell comes in and thinks about, well, if I have an ideal gas, all these molecules are whirring about at different speeds, but they're not all going at exactly the average speed. So the average speed tells us something about the energy in this gas, but it doesn't tell us everything. Are there a lot of fast molecules and a few slow ones, or are they all really close to the mean? How does that distribution look like? Kind of more detailed information. And he derived this distribution for the energies of an ideal gas. And this, in some sense, is kind of the birth of modern statistical mechanics. Now, Boltzmann also came along and built further on this idea and really connected these microscopic states, this detailed information about how all these little atoms, little molecules are moving around, to the big macro picture, which is, as the human level, we see, okay, a big box of gas, it has some pressure, it has volume. How do these quantities relate back down to all the microscopic details? And he also drew this connection as entropy as a sort of uncertainty. So a macro state is something we see, like the pressure and volume of a gas. And he connected that to these micro states. He said, well, if that macro state has a lot of different micro states that could have given the same macro state, then it has a higher entropy because we don't know which one of those particular microstates the gas is in at any given time. So that a little bit, has drawn this connection between thermo and stat mech, and that's just continued to grow, and now into the modern era with quantum thermo.
So I have two questions, I guess, with respect to that. So the word thermodynamics, thermo implies heat, but it's more than that. It's really a study of energy and energy transfer. Do I have that correct?
Yes, exactly. I mean, historically, it was sort of like the main thing to study, but there's sort of a nice line in this one textbook for thermodynamics, the Callan textbook. It says like, well, energy isn't special sometimes in the way it's treated. So we often write things in terms of energy, and it plays this kind of seems to play a privileged role. But it's really any extensive quantity. So whether it's energy flowing, whether it's angular momentum being exchanged between two spinning tops, whether volume is being exchanged between two gases, it could be sort of any quantity. They all obey these sorts of laws that can kind of generalize from just the exchange of energy through heat and work.
So heat is, as I understand, kind of a random process, whereas work is more of an organized process. So energy transferring in heat, it's not a directed process, whereas energy transferring through work would be like a defined process, I guess, basically.
Yeah, it's like heat and work are both kind of ways of changing the energy of something, like heat or giving work to a system. But heat is kind of unorganized energy. So it's difficult to harness it for some sort of useful task unless you have other auxiliary systems to help you do that. Whereas work is something that's very ordered. It can be directly converted into other forms of work. It lets us do useful things like charge your battery, push a car, raise a weight. So as you say, work is a sort of like organized, ordered energy, and heat is like this random, sort of entropic, unuseful energy.
So you mentioned statistical mechanics. I wonder, so I understand there's a connection between information theory and thermodynamics. Can you maybe just talk a little bit about how that came about?
Yeah, and really, I think one of the central concepts there is this notion of entropy. So entropy studied thermodynamically as what I mentioned with Boltzmann's idea of as like counting the microstates accessible to a system. And from seemingly like a very different direction, we have entropy in information theory. This starts with the work of Shannon and is built upon later work of von Neumann in the quantum setting. And that entropy is also a measure of uncertainty and disorder through a very kind of abstract lens of saying, well, I just give you a probability distribution. I have a bunch of different things that could happen, and I give you the odds that any one of them does. I can assign an entropy to this distribution, and it tells me something about how difficult it is to compress that information, and it has this kind of different flavor. But there's very deep connections between the two. So if you write down the right probability distributions in thermodynamics and you compute their entropy with Shannon's kind of information theoretic formalism, you find that, oh, this is giving me the thermodynamic entropy. And so there's this kind of deep connection that really these are very intertwined quantities. And there's sometimes debates like in certain thermodynamic settings, it's like, are we using the right entropy? Is this really the right one to use? But largely speaking, in many scenarios, the information theoretic entropy and the thermodynamic entropy do coincide. And it's kind of interesting fact of nature, really, that this entropy quantity plays so many different roles.
Yeah, interesting to think. And of course, maybe we'll talk a little bit about the connection to quantum computing at some point. But I understand, is it true that information can turn heat into work? Is that statement correct?
Yes, and be careful what exactly we mean, but in a setting, but basically yes. So we're talking about heat as a sort of undirected, unuseful energy, right? But the casual listener will say, well, of course that's not true. I heat up like an internal combustion engine, I get a lot of heat and I turn that into work. My car is driving. Well, that's true. So we're going to be very careful. Like, what does it mean when we say heat is unuseful? Well, what it means is if I have work, so let's say I have a battery that's a source of work. What I can do is I can build a contraption that takes that battery and it changes the state of the battery in some way, and it drives a car forward. And nothing else in the universe changes. Then that's really important. So just by changing the state of the battery, I'm able to do work and push a car. But if I want to use heat to do the same, so now let's just say I have a hot, like an internal combustion engine, I've just sparked the mixture and I have like a hot gas and I want to extract the energy. There is no process, and this is one statement of the second law of thermodynamics. There's no process by which I can just take the heat out of the gas and turn that into work so that at the end I'm left with a slightly colder gas and a car that's moving forward. What I need is another kind of piece, which is a cold reservoir, which in all our kind of machines, like implicitly, it's the atmosphere. So I take the hot energy from the gas, I turn a little bit of it into work, where a little or a lot depends on the details of what we're looking at. And the rest of it is dumped as this waste heat into the atmosphere. So I'm taking advantage of this temperature difference between hot and cold. And heat would anyways flow from hot to cold, but I'm sort of able to skim some off and extract work from that. But at the end of the day, my car's moving and my gas is colder, but I've changed the universe in a way because I've heated up this cold reservoir. And so that's how we get around the second law. We say, okay, well, I've changed the state of the universe. So, you can extract work from heat, but it requires this additional something else, right? And as you say, that something else could also be information instead of a cold reservoir. And this relates to some ideas listeners may have heard, things like the Maxwell's demon, which is this idea that actually information has a thermodynamic presence. It isn't just something we can abstract away and say that, oh, the information doesn't count, it's just in our heads. Writing down information even on a strip of paper, zeros and ones, this memory, initializing that memory and then possibly erasing it. These are physical actions. They must really be done on some information processing device, whether our brains or a computer. And that has a thermodynamic cost. And so it's perhaps, that it becomes a little less surprising that, okay, information can actually really help us, as you say, like turn heat into work.
Yeah, then maybe we can talk about Maxwell's demon a little bit. Maybe in the next question, which I have, is if you could lead us through a little bit about the laws of thermodynamics, the first and second law, I guess, in particular, and how the first kind of relates to the second, and maybe how Maxwell's demon comes into that question.
Yeah, absolutely. So the first law is conservation of energy. This says I have a system, and if its energy changes, this must come from the work and the heat that go into the system. And, people have kind of recognized ideas like this for a long, long time, even before Clausius and Carnot really put it in exactly the sort of modern formula. But it's a very sort of intuitive idea that, like if we think of grains of sand somewhere, they're being moved in different piles and all that, but the total amount of sand isn't changing. Total amount of like this energy isn't changing. And what's interesting though is that the work and heat can change kind of very drastically. So I can have a process where I put in a lot of work, but I extract a lot of heat, or vice versa. And the internal energy doesn't change because these two effects cancel each other out. So it's important to understand that basically if I, start with my system in some state, it has some certain energy, and I end up in a different state, now my system has a different energy. And it doesn't matter what happened in between, but I can just say, there's a change in energy between the two systems, initial and final time. And I could have done some different process that ended up with the same final energy. But the heat and work could change very drastically depending on what kind of path I did. So maybe I just don't do anything and the heat and work are both zero and I have the same final energy. Or maybe I put in a lot of heat, but then I extract work and still the final energy is zero, like there's no change. So here the energy is like an internal property of the system. So if you look at the system at a given point in time, it has an energy. So that's like an internal thing, and we can look at changes in energy. What heat and work are what we say sometimes like path dependent. So we don't say like a system has work. We say that we start a system in some state and it ends up in a different state, and it follows a particular path there where we did some amount of work on the system and also possibly put in or took out some heat. But these two path-dependent things, work and heat, together combine to give us something that's path-independent, which is just a change in energy.
Okay, interesting. And so the path dependency, I'm thinking about that as like an actual path through space and time. Does that make sense?
Yeah, I think sometimes we abstract away the space part and we're just thinking about like trajectory through time. But basically, yeah, like whatever, the system start off in some state and it follows some trajectory to another state. And then we say it's path, right? And we think just in time, or if you have systems moving around, then also in space.
And so the second law of thermodynamics says that you can't go from a disorganized state to an ordered state or an organized state, I guess, essentially. And how does that kind of relate with this Maxwell's demon idea? I guess Maxwell's demon, as I understand it, there's a demon, not an evil character, but just a character
Yeah,
that,
sort
that
of a
sits in a
cartoon
box
demon, yeah.
with a partition and can control that partition in the box full of gas and control the
Mhm.
distribution of gas. So maybe just explain that a little bit in the context of the second law of thermodynamics.
Yeah, absolutely. So the second law, there's various different ways to formulate it, but the one simple one is to say the entropy of the universe never decreases. It's always going up. You may think you win in some corner of the universe because you say, aha, I reduced the entropy here. But if you do your bookkeeping carefully, you see that somewhere else, you've increased the entropy by as much as what you've decreased it. And so in some sense, there's no winning against entropy and disorder. But you're really careful how exactly you formulate this statement, right? And there's other ways to formulate it. So another way to state it is to say there is no process that just takes heat from some hot object, converts that into work, and has no other effect on the universe. That's another equivalent statement of the second law. And so Maxwell's demon, the issue there, I mean, why is this paradoxical? Why is it so interesting? Is like, well, it seems to violate the second law, which very shocking. Like, as physicists, we really believe in the second law. And so what is the idea? As you kind of said, we have a gas of particles just at a uniform temperature. So that's kind of our hot reservoir. And what we have is like a very nimble fingered demon who has this little partition he can open between the two halves. And, when he sees a hot particle going through, he lets it through to the right side. And if a cold particle ever comes close, he lets it through to the left side. And so without doing any work, over time, we build up to what was initially a uniform temperature gas, becomes a hot and a cold one. And now, like we discussed, like with an engine, like a car engine, we can actually harness this temperature gradient. So we can take the hot and cold, let heat flow, skim off a bit of it to do useful work. And at the end of the day, we're left with, again, a uniform temperature gas. It's a little cooler than before because we skimmed off some of the energy and we did work, but there was no other change in the universe. So it seems like we violated this second law. And it took a long time to really understand, like, what is the resolution to this kind of paradox? Why does it seem like we can violate the second law? And this sort of, I'd say two explanations that I particularly like. So the first one is the sort of Feynman's ratchet idea. And this kind of says, what if you tried to build such a device sort of autonomously? And all I mean by that is, let's just say you tried to build a kind of gadget that doesn't have any like computer parts, no microchip, nothing. It's just some sort of cool contraption that, maybe like a trap door that only opens one way for hot gases and not the other way. So no sensors, no information processing, but just some kind of clever contraption. And what Feynman envisioned specifically was a ratchet. So what is kind of important there is that a ratchet is something that kind of breaks reversibility, because like a ratcheting wrench, it ratchets one way, but the other way it tightens a screw. And at the microscopic level, if you can kind of break reversibility, you can build a kind of very small ratchet, then you can kind of break the second law, because you can do this exact thing with the hot particles going one way, but this trapdoor is staying shut for the other direction. And what was really interesting is that Feynman showed, okay, what would just a ratchet have to be? If we just think like it has like little, little teeth on some sort of like strip, and there's like the ratcheting mechanism with some sort of spring, and it stays down, and sometimes it pops up, and then it's able to move. Well, if it's really sensitive enough to move for little molecules, right, coming through, it has to be very, very, small and very light. And what that means is this ratchet itself is going to fluctuate thermally. So, people that kind of abstracted away that said we have this ratchet and it's a perfect ratchet and it does this thing. But Feynman said, you need to be careful, because what would a perfect ratchet mean? It means no vibration, nothing. In other words, you're putting it at a very cold temperature. So implicitly, you're saying I have a very cold ratchet, then I can do this extraction. But what you find is actually there's going to be heat transferred from your gas into your ratchet. And so you've kind of cheated, because you've taken a hot system, you've added in a cold system, and now we're back to the usual setting. Heat goes a little bit from hot to cold, you skim off a little bit and get work. And so this is where the bookkeeping has to be very, very careful to see, like, where does it seem like the second law is going wrong? What have we failed to account for?
And I guess the demon in that sense, this imaginary character sitting in a box full of gas, has to remember which
Well,
particles are hot and which are cold, right?
yes, for the sort of second formulation I was going to say, and I was
Right,
even before getting there, this is sort of saying let's even try to avoid keeping information and just
right,
build something that kind of passively does the job without a
right,
memory. And that doesn't work, because any mechanical device is itself going to be subject to thermal fluctuations. So in other words, this trap door will sometimes open the wrong way, and we're never going to win, basically. We're
right,
never going to build up this temperature gradient.
right. And the opening and closing of the trapdoor uses energy itself. That's kind of the ratchet idea, I guess.
No, so
No,
there you
okay,
can kind of abstract away. You can say, imagine it's like a very
right,
light, very small trap
okay,
door. So it doesn't take energy to move it, but to perfectly open and close it for the molecules, you need like a very cold ratchet, and that itself would violate the
right.
assumptions of the second law, and that you're just using a hot reservoir. And now we can talk about the scenario you're considering, where let's say, okay, the passive system didn't work out. Let's build something more clever, and let's have like a little daemon, a little camera, and some computer processing that opens and closes this trap door, and that'll work perfectly. And it will. That one will really work out. And we say, it looks like we're violating the second law. What's going on? And here, as you sort of alluded to, it took a while to figure out, and it was really Bennett who sort of nailed this down. It's the information processing that we're doing that actually has a thermodynamic cost. Because let's say the daemon starts off with no information, no memory. After doing this process and tracking the hot and cold particles, at the end of the day, we've done all this work, we've built up our temperature gradient, and then we let it flow and extracted work. So what have we done? We've extracted work, we've cooled the gas, but, like I said, has the universe changed? Has anything else changed? Well, yeah, I mean, the demons, his mind, the memory, however you want to build the demon, that's changed. So, strictly speaking, we have to restore all of that if we say like the universe should be back to the way it was. And there is kind of the kicker, because erasing the demon's memory incurs a thermodynamic cost. So, sometimes called Landauer erasure. There's a cost to erasing information, which again, very kind of unintuitive in some sense. And like, now the benefit of hindsight and thinking about it for so long, it seems so natural, but it's really a very, very kind of counterintuitive idea that like abstract information doesn't really exist. It's always written down somewhere. It's always stored somewhere, and physical things obey thermodynamics. So information is governed by thermodynamics.
Yeah, interesting. And yeah, I guess we think of information as a kind of an immaterial thing, whereas energy is a material thing. And so how do they interact? It's maybe makes me think of the quantum observer effect in terms of if you make a measurement, and I wanted to ask about measurement in the context of quantum thermodynamics, but if you
Yeah.
make a measurement, you actually change the system. So that measurement is information, but it's not a physical thing, and yet it's causing a physical change.
Hmm.
So maybe let's move to quantum thermodynamics. So how do we get from classical thermodynamics, the second law in particular, how do we put that in the quantum realm? So classical, I understand, is kind of at the macroscopic level, the level we can see and physically sense.
Hmm.
whereas quantum thermodynamics is at the microscopic or very tiny level. How do you take classical into quantum? And just maybe if you could outline how the study of quantum thermodynamics came about.
Yeah, and this sort of interesting. There's kind of like there's like an in-between step that's sometimes neglected, which is even just classically, what the stuff we've talked about is basically equilibrium thermodynamics. So we're thinking about large systems, their internal degrees of freedom have all equalized. If left alone, they wouldn't evolve any further. But there's a step there where we just say, even just keep things classical, but let's talk about really small systems. So, really, really small, like nanoscale motors or even things in our body, right? So small proteins folding and unfolding. And these systems are nowhere near equilibrium with their environment because they're being kicked around. There's lots of things going on. They're very small systems, so the thermal fluctuations really have a large impact on them. And just understanding this sort of non-equilibrium thermodynamics is, a whole area of research, and just classically. And this is about taking the ideas of these equilibrium things and going now to small non-equilibrium systems where they aren't, well, at equilibrium with their environment. And there's all sorts of new effects there. So when we say things like the free energy, which is like the sort of the useful energy inside in an object, how do you even define that for something that's not at equilibrium? This is something that's being studied and so forth. So there's sort of that step to small non-equilibrium devices. And then there's like the further step to say, well, what if not only are they non-equilibrium, but the laws of quantum become relevant at that scale or at that temperature? And that's when you get to quantum thermodynamics. So there's sort of two, there's already it's more complicated than equilibrium thermodynamics because you have these non-equilibrium effects, which you could even have classically. But on top of that, we're really thinking about quantum effects, even on top of that. So there's kind of these two big differences from the usual classical big equilibrium thermodynamics.
And what launched the study of quantum thermodynamics? When did that study really take off?
Yeah, I think in some sense, the linking of quantum and thermodynamics goes all the way back to Planck and this sort of like UV catastrophe. So there were certain like classical predictions for the energy from a black body, and the catastrophe was that the theory prediction said there'd be infinite energy at small wavelengths, and so obviously it was nonsensical and didn't agree with of course, the observed data. This idea from Planck was say, what if we quantize this radiation? It's quantum, that's really the origin of the term. That actually results as UV catastrophe, and it gives the predictions in line with like the Rayleigh-Jeans law, and it's like, okay, this is all kind of sensible. So that's sort of the first, around the turn of the century, this like connection between quantum and thermodynamics in some way. And there's some ideas about like quantum statistical mechanics, and instead of ideal gases, what if we study quantum ideal gases? But in sort of more recently, so I'd say something like maybe the last 30-ish years, it's been thinking about thermodynamics and specifically with quantum information. So not just really the thermodynamics of quantum mechanical systems, but a little bit more quantum information tools applied to study thermodynamics. And so similar ideas, but a little different focus or a little different emphasis on what's studied and the kinds of questions we ask. So in quantum information theory, a lot of the tools are things like, well, obviously, so there's like Hilbert spaces and this linear algebra is sort of mathematical background. But there's a lot of different techniques that we think about. So things like resource theories, where a resource is kind of something useful, and we ask, well, how can we convert this resource into other forms of it? What sort of states, if I give you a system, is it resourceful or not? What can I do that doesn't change the amount of this resource? And it's like kind of one way of thinking. A lot of different quantum entropies, and again, very closely tied to the information theoretic entropy. So we talked about Shannon entropy. That's actually just one in a whole sort of, family or entire zoo of different kinds of entropies that are relevant for different tasks. And so finding connections with these to thermodynamics is a big area of research. And so there's all, many other kind of tools in quantum information theory, majorization, there's quasi-probabilities. All these different tools have been sort of brought to bear on the thermodynamics of these small quantum systems.
Fascinating. So it's really taking that classical thermodynamics and taking it closer to the first principles. Is that a way of seeing it?
I think I mean, it's kind of very interesting. So thermodynamics is sort of so one thing, what's one thing remarkable about quantum thermodynamics is like, like what changes. Well, in many ways, many things don't change. And that's kind of incredible. Like there are statements of the first law, of the second law. And this really points to thermodynamics as being, almost like a meta theory, in that sometimes like the underlying physics may change or may be updated, but thermodynamics is almost on a level even above like the details of the theory, where it's like, no, the second law will still hold. So, I mean, for example, like thermodynamics was first developed before relativity. And yet, even if you do the correct relativistic calculations for, say, like for certain gases or certain like cosmological phenomena, even black holes, you still find that, oh, this like second law is obeyed and like the first law makes sense and all that, right? And like, something like thermodynamics were formulated far before relativity and before quantum and before, whatever other physical theories mankind comes up with in the future. But sort of still expect the second law to hold in whatever way it's formulated, whatever the underlying physics is. So it's kind of really some miraculous feature of the theory, that it almost doesn't really change. It doesn't need to be updated based on the underlying physical models, even if those models change with time. The sort of core tenets of thermodynamics, they're so profound, they're so fundamental, and they're so kind of devoid of details that they stay. They have this kind of permanence over all the other theories.
Interesting. And so you mentioned quantum effects, and so I guess there's a lot that still remains to be discovered in the quantum realm. And from my non-scientific understanding, but I think of the quantum as the smallest amount of energy that can either cause change or be changed.
Mhm.
And so when you say quantum effects, when you're looking at quantum thermodynamics, I think of quantum effects. Perhaps most people think of when you hear of quantum effects, maybe entanglement and superposition, like entanglement being the connections of these quanta of energy, and superposition
Mhm.
being what happens to one quantum, the same thing would happen to the connected quantum at the same time. And you're putting that in the thermodynamic sense, taking those two effects, entanglement and superposition.
So I think, the word, as I said, so quantum starts off with this idea of like Planck's quanta of energy, and that's kind of the origin of the term. Sort of now, when we say like a quantum system, we don't necessarily mean just like a unit of energy anymore, but the term is kind of broadened to mean just any system. Everything is in principle governed by quantum mechanics, but what we really mean is a system where the quantum predictions become sort of relevant, right? So this is a little bit like saying, everything is governed by relativity. So I mean, just like special relativity. So if we're going fast enough, we should see time dilation and length contraction. But, even on the highway, we're not hitting speeds anywhere close to where that's relevant. And so we can just stick with Newton's laws, right? So like Newton's laws got us to the moon, and that's, it's a good enough approximation at that scale. And so similarly, classical quantum physics in principle always applies, but you don't always have to go through that much work. You just stick with the classical predictions. But for some systems, the quantum effects are really relevant. They're really large. And so if you do the classical prediction, you'll be off. It just wouldn't give you anywhere close to the real observed, whatever you've seen in an experiment. So there you can say like, okay, by quantum effect, we just mean effects that don't show up in the sort of classical world, in the classical setting. So as you say, things like superposition and entanglement. And indeed, like a big part of quantum thermodynamics is understanding, what do these effects do? Does entanglement, how does that corroborate with the second law? The superposition affect how we think about the first law? Like it's exactly understanding like what is different with these quantum phenomenon. Can we draw analogies to the classical world, and what things are just fundamentally different?
Right. So I guess, yeah, quantum could mean essentially microscopic, not necessarily the tiniest, smallest quantum, but more at a
Yeah,
microscopic level.
exactly. Because we can
Okay.
think even about like nanoscale motors, for example, or like certain things even in our body, which is not at the scale of atoms, but even at the scale of molecules and like that, that sort of mesoscale, quantum effects become relevant.
And so what sorts of things are being discovered or could be discovered at the quantum thermodynamic level, for example, with respect to entropy? We've talked about entropy in terms of entropy being that order never increases over time. Physical systems go to maximum disorder, I guess, over time. So does that still hold at the quantum level, or do things change when you start to look at things at the quantum level?
Mhm. So the short answer, yes. Like systems still obey the second law and they still tend towards this maximum entropy. But, just like with the Maxwell's demon, the accounting has to be done really carefully. And, these two quantum effects that we've been talking about, superposition, this idea that you can have sort of a system in two states at the same time, and entanglement, which is like this very powerful correlation between two quantum systems. Both of these can sort of act as a fuel to let you do something that you couldn't do classically. So you can, for example, sort of burn coherences, and coherences is just another way to really talk about superposition. You can burn these up to actually perform work. So I start off with a state that has some coherence, and I end up with a state that has less coherence or sort of less superposition, to put it a little loosely. But in the process, I've actually done some useful work. And by work, I really just mean like in the classical sense, like I've raised a weight. So not some sort of mystical like quantum work. It's like, well, is that even useful or not? But no, like real work, like pushing a car. Now, of course, quantum systems, the size they are, you're almost certainly not pushing any car. But in principle, you've extracted, you've raised some sort of weight, even if it's a fraction of a meter up. But you've really extracted real classical, usual work in the kind of intuitive way we understand it from the coherences in a quantum system. And that's very interesting. It tells you have to kind of do careful accounting, because if you just try to reason classically and if you write things as a matrix, not to get too mathematical, but you could think about there's a diagonal in your matrix, which is some numbers you write down. And then there's numbers you write off the diagonal. And this kind of represents your quantum state. It's these numbers that are off the diagonal that are getting smaller. So when they're large, there's a lot of coherence. And when there's less coherence at the end, those numbers are getting smaller. Let's say they even just go to 0. But classically, we just think about the numbers on the diagonal. And so if you're only looking on the diagonal, you would say, well, I started and ended in the same state. I didn't see anything change, because you weren't tracking those off-diagonal elements. And you say, well, and I've extracted work, and I violated the second law. But if you really look at it carefully, something's changing. And what that is quantum coherence is being burned. And in a similar vein, now there's something very cool with entanglement, or even just correlations between two quantum systems. And so we're familiar with a very conventional idea that you take a hot and a cold object, heat flows from hot to cold. Simple. But actually, if you can start things off where you have a system that's hot and a system that's cold, quantum systems, but they're entangled. So if I just gave you the hot system and you were in the lab, you did every possible measurement on it, you would say it's a hot system. You wouldn't know the difference, is it entangled or not. And I give someone else the cold system, the same thing. They can do any measurement they want. They can probe it however they want. They would never know that it's entangled with something else. They would just say it's a cold system. It looks cold to me. And so you have your system. You're convinced it's a hot system. Someone else is convinced it's a cold system. And you bring them together, and voila, heat flows from the cold system back into the hot system. You would say, wow, what the heck's going on? It seems like we've violated the second law. Then maybe you guys get really careful. You get together and you say, well, let's really measure what the state of our joint system is. And you would find, oh, it's not just a hot and a cold system brought from nowhere and brought together to interact, which is what the second law assumes in this particular setup. It's actually an entangled state. So they have some very strong correlation. And if you write down the second law now, it says that this information that's shared between the two, the mutual information, you have to account for that in your bookkeeping. So when it seems like the entropy is decreasing and heat is flowing from cold to hot, if you, again, do this kind of global accounting, you see that, okay, that's, first of all, it's okay because you're actually burning this entanglement to kind of reverse the flow of heat. But also, if you see how much information you have to burn to do that, that also obeys the sort of second law thing. So you're not getting away by like to now reflow the heat back. You're never going to gain more information than what you burned. So again, the second law is obeyed. You have to be very careful with like the sort of accounting for these quantum effects or even just classical correlations between the two systems.
That's really fascinating too. And I think you paint a really interesting picture. So if I understand it correctly, you're accounting for the individual causes and effects in these systems and the points of balance. Is that do I have that picture?
Yeah, I would kind of frame it as like you're accounting for ways in which the state of the system is different from just the classical thing of no coherences, or if the very simple setup with no correlation, so a hot and a cold system completely uncorrelated. And you're trying to say, well, what if there were these correlations, these coherences, quantum entanglement? How does that lead to modifications of the second law? And what do these things are basically now resources, because it's like a fuel that you have that you haven't accounted for. And so this entire theory, and this again where the resource theory kind of picture comes into play to say, well, okay, like a number in a matrix is a number in a matrix. It's an off-diagonal like number, but what does that physically mean? What does it tell me? How much weight can I raise with that? How much work can I do? And so really just quantifying this, or like entanglement, right? Like how do you quantify it? Okay, and there's various quantifiers out there, but then what do those mean? Like this kind of, it's a kind of like a language for converting like entanglement information into how much work does that translate to? It's sort of like a dictionary to go back and forth between the two.
Interesting. Yeah. And so that diagonal line that you mentioned, that would be is that the point of no coherence?
That's kind of like the classical bits
Yeah.
of the state. And like
Right.
if you just probed it classically, you would only see this diagonal part. And then these off diagonals would be kind of invisible to you. And you would say, well, oh, nothing's changed. Seemingly.
Yeah, interesting. And so does this tell us anything about limits? And you mentioned resource theories, and I think that's part of my next question. But as I understand it, that kind of talks a little bit about limits. So in terms of when you get down to these really macroscopic systems, do we understand more about limits in functions, I guess, that are causing these thermodynamic changes?
I think certainly one limit that we kind of learn about, and we definitely want to check, is to say, well, if this quantum system gets bigger and bigger or really hot and kind of approaches now the regime where it's basically behaving classically, what do our results tell us? What do they converge back to? Because we have a pretty solid understanding of what happens for large classical systems. And so it's a kind of a really important sanity check that whatever we derive should, in the limit of classical systems, give us the same results as, what we already know. And that's like a very important limit to look at.
And I understand that there are different ways of looking at the second law of thermodynamics at a quantum level. I think we've actually talked before, I think about the second laws, I think is what something that you mentioned.
Yeah, yeah.
So it's not changing the second law itself, but it's different configurations of the second law. Is that a way of thinking about it?
Yeah, so this is a very interesting result from Brandau and others, which is this paper called The Second Laws, as you say, of Thermodynamics, plural. And I mean, what's one way to think about the second law? We can think about it as sort of a constraint on the allowable processes in the universe. Like it just outlaws certain things. As that there just is no process that, just takes heat, turns it into work without any other side effect. And, what Brandau and others found is this kind of interesting set of constraints to say that, well, for certain processes, there's actually multiple constraints. So there's like a second law constraint, and there's another one, and another one, another one, and all of these come from different entropies, like a family of, I think, the Renyi entropies. So it's sort of interesting, I guess, that like these quantum systems permit these like various second laws, and that there's like all these stronger constraints on the processes. And it doesn't quite say that like, okay, quantum processes are like more constrained than classical ones, but it's certainly interesting that like this is the sort of landscape for quantum systems, right? That there's the entire family of these constraints for different Renyi entropies, different alphas. And sort of related, and to go back to, a little bit to your earlier question, we can talk about some of the, the recent work I've done with my collaborators, where we're also studying, well, what does entropy even mean in a very quantum regime? And we're studying, so a little bit different than what we've been talking about, is actually at the stochastic level. So what I mean there is to say, well, how much does the energy of something change? What does that mean? Maybe I have some experiment. I start off some way, I do something, and then I measure the energy before and after. Maybe that varies. Maybe there's some randomness, there's some fluctuation. So I do this experiment, I say, okay, the energy changed by 1 joule. I do it again, it's like, oh, only half a joule. But I can do this a lot. I can just repeat it many, many times, and I'm going to build up some statistics. And I'll find that, okay, on average, the energy change is equal to something. But there's a lot more information there. There's information like what's like the standard deviation of my energy measurements, or the variance, and what about the moment generating function, and all sorts of statistics you can do if you look at the whole distribution. And so broadly, when we say stochastic, we mean really think about just doing the experiment once. start and end, and you get some statistics. What are you reasoning about with those? What do those teach you about the physics? So what me and my collaborators look at is exactly this kind of setup we talked about with the hot and the cold object. And we said, okay, let's even forget about correlations between them. So let's assume there's no entanglement, there really is a separate hot and cold. What changes if now these systems are quantum? And instead of just exchanging heat, which you can go and you can measure the energy that's being exchanged, what if they're exchanging some really quantum stuff, which would be non-commuting quantities? And non-commuting just means you can't go in and measure these two things at the same time. So to contrast, classically, you could have, a hot and a cold balloon. And not only are they exchanging heat, but maybe you tie the necks together and they're exchanging particles. So one's filled with one gas and a different kind of gas. So particles and energy are flowing back and forth. But, with sufficiently good lab apparatus, in principle, you can go in and measure the energy that's going back and forth. And at the same time, you can track the particles. So you can do all these measurements at the same time. But in our quantum setting, there's actually like observables, things that you can measure, but there's a pair of them that you can't measure both at the same time. So you can pick one, you measure it perfectly. You can pick another one, measure it perfectly, but you can't measure both perfectly at the same time. And this is sometimes called like the Heisenberg uncertainty principle. So in this setting, how do you now talk about the entropy production? Because, you expect there's a contribution in the classical, like there's a contribution from the energy flow, and there's a contribution from the particle flow. Here, if you have two things, and for example, we could have two quantum spins being exchanged in like the X and Y direction. How do you talk about the entropy production? What changes? And in short, we find that actually the very definition that one typically uses for the entropy production, classically, actually gets updated because there's three different formulas that are completely equivalent classically, and you can write down the single definition in three ways. But the three formulas are actually inequivalent in this very fundamentally quantum regime. And each one can be taken as its own definition of what the stochastic entropy production is. And each one kind of teaches us something really interesting about the underlying transport and how quantum kind of affects it. And to kind of now tie this all back to what we were talking about with coherences and superposition and entanglement. So the result I'd mentioned from this paper about kind of reversing the arrow of time, which is to say with a hot and a cold object, if you entangle them, you can actually find heat flows from cold to hot. What we find is in a similar way, there can actually be negative entropy production, but the systems don't have to be even correlated. It's enough that they have coherences on their own. So it's kind of in any of the analogies, kind of pretty precise in terms of the equations. But basically, these coherences are also playing a role of this kind of creating some, surprising, unintuitive, very counterintuitive quantum effect where, entropy is negative, but actually we thought entropy would always be positive in this scenario. I wouldn't say second law is violated by any means. I just think it, in the same way, it's carefully write down what does a second law state, what are the assumptions, and are we doing careful bookkeeping of everything that's going on?
So those three different inequivalent equations, I think you call them, what would that lead to? I guess knowing that there's that inequivalence, what would a potential significant outcome of that be when further research is done?
Well, I think for me, it sort of raises the question immediately, like, is there something more fundamental than? Like, is there sort of a unifying way to understand these three definitions that, kind of puts them all on sort of an equal footing and says, well, depending on the context you're studying, this or that definition is more relevant. Certainly, it tells us that depending on what kind of system you're studying, one definition might actually be more useful than another to really understand what's going on. And really kind of explodes this expectation that, like in the classical setting, these are all equivalent formulas. And it's like, well, now they're not equivalent. So really, like, what is the right one to use in the right context? And how can you kind of get there from a first principles thing? It kind of really raises these sorts of questions. And we should have hope in this thing we're looking at that some of these definitions might be useful for certain contexts. So for example, if we're studying now kind of quantum engines, instead of just the classical steam engine, how do quantum effects play a role? Do they help with engine efficiency? This is something that's been studied a lot in the field, and we wonder if our definitions can kind of help shed light on how these quantum effects and non-commutation can help or hinder engine performance.
And that maybe leads into my question about quantum steampunk, that rather exotic sounding, I guess it's not a field, but an approach to maybe studying quantum thermodynamics that Nicole Younger-Halpern, who you're working with, is leading. And maybe if you could just explain how the idea of quantum engines, resource theory, and the other focuses of quantum steampunk are coming together in this whole area of quantum thermodynamics.
Yeah, absolutely. Well, let's talk a little bit like quantum steampunk and quantum thermal, like what are some of the areas of research? What are some of the big open questions? So, one thing we talked about is actually, I said, like the first law and second law, it's surprising that you could write it down for quantum systems and, they kind of stay the same. And that's true, but there are actually just very basic fundamental open questions in quantum thermal. Like, how do you define the stochastic work for a quantum system? Just kind of, you'd say that's almost like even preceding the first law. It's like you have to first define, like, what do you mean by the stochastic work? And actually, like, there's various proposals, but no single proposal has all the kind of properties that we would want and all the desirable classical limits. But at the same time, there's also these no-go theorems in the last few years that have said, actually, if you want to define work in the quantum setting that satisfies certain reasonable axioms, you can't. It's just impossible, provably impossible. And so the question is, like, for the community, where do we go from there? Do we drop some of these assumptions in what we want for stochastic work? And, which assumption do we drop? Or do we just accept that we'll have to use different definitions of work in different contexts? Like, do we just have to give up the sort of universality that we're so used to in the classical setting? It's not clear. I mean, these are really just like very basic, very fundamental questions that are still open and a topic of debate within the field. Then there's, within the resource theory idea, and definitely relating to Nicole's like quantum steampunk work, is a lot of stuff about quantum engines and resource theories and extracting work now from correlations, coherence, entanglement. How can we extract this work? What are the ways we can convert it? If I have 2 copies of the system instead of just one, can I do better than twice the efficiency? So obviously if I do what I did on one system twice, I can get twice the energy out, but can I do even better than that? So if I have many copies of the system, can I somehow win by using them in, a complicated way if I use 2 together? So these kind of questions about, how do things in a single shot, so the single state versus 2, 3, and many copies of the state in the asymptotic regime, how do those results interrelate? This is also kind of very closely related to information theory and thermodynamics, where we talk about like things in the single shot regime, if I just do things once versus many times. So like if I flip a coin once, if it's heads or tails, you're not surprised either way. But if I flip it 1 billion times and I'm, getting close to 1 billion heads, you're pretty sure it's a biased coin, because there's no way it's not close to 500 million each time, right? And so that very simple idea plays into both information theory, but also then thermodynamics when we think about entropies and we think about physical tasks, like really doing something on a state. And we say, well, mathematically, it's easier to understand that if I had 1 billion copies of the state, here's what I could do. But in reality, and any experimentalist is not going to like it if you tell them, hey, do this 1 billion times. If I just have 1 copy of the state, what can I do? How much fluctuation is there from the average result if I did it many times? Just understanding this in general is a kind of active thing in thermodynamics for many tasks, understanding what the single shot regime looks like and what different entropies come into play from what's true for many copies in this asymptotic limit. And, earlier you mentioned measurement, right? Understanding how measurement and subsequently feedback can actually play a role in the evolution of quantum systems and what that means for the thermodynamics in terms of tracking, the information that we're putting in and potentially the work that we're getting out is also a really cool area of research. So these sort of like monitored systems or weekly continuously monitored, depending on how you want to do your measurement and feedback. But unlike classical systems, the additional layer of complexity is that, yeah, you measure the system and you change it, you do some process and you process, some sort of feedback control. But the very act of measuring is also disturbing the system. So you have the disturbance from measurement, but also then you're trying to correct it in some way. And so there's this cool interplay of, how measurements versus just letting the system evolve. How do those interrelate? What kind of new effects go there? It's another kind of very active area of research. And that actually touches a little bit too with quantum computing, where there's studies of these sorts of quantum circuits, which basically you can think about like, in a quantum computer, you start off with some qubits, quantum systems, and you let them evolve in some way. Think of that kind of like a free evolution. It's unitary, it's reversible, they're evolving. But now we start asking what happens if I intersperse this with some measurements? And it turns out that like the frequency and how you intersperse with measurements can lead to some very cool effects and some phase transitions. So these kind of very interesting ideas showing up across multiple fields. Yeah, and then maybe like one other like kind of pillar of like this quantum steampunk, quantum thermal I mentioned is really kind of building and thinking about useful practical devices. So one thing I know that's been worked on in the group is like quantum cooling and quantum refrigeration and understanding how actually by using some sort of quantum reservoir, which again is a little bit different than the second law statement because you say my reservoir might be prepared in some special state, not just like an equilibrium reservoir. How can I possibly harness this to do cooling more efficiently or, to possibly power an engine more efficiently if I have like squeezed states of light, some like very non-classical states of light, and that I'll try to harness in some way. So these kind of questions like basically practical devices. And especially I think one thing that's important in quantum thermal moving forward is to get more and more experiments out there, really kind of probe this stuff in the lab because there's, a lot of theory, but then bringing that to something that's really testable, that can show you something cool in the real world, I think is really important.
And are you working mostly then on the theory, or are you also doing the experiments?
So I'm not doing any experiments. I'm definitely on the theory side of things, but we have some collaborators with some excellent experimentalists that really cool to see our ideas, being done in the lab. And
Yeah.
I think really when you work with an experimentalist and you really try to get things done, and on one hand you have like these very, fancy equations, but on the other hand you just have raw data from a lab with noise and with experimental imperfection. Just trying to really connect those two and understand them, I think is like really good physics. Like it's just I think in some ways that is real physics, right? Because that's what takes it from being just this kind of math abstract stuff to like, no, this is the real world, and like I can understand your data, not just like a simulation of your data that's all perfect, but no, your real data, and I can see, okay, some dominant source of error. I can see, okay, this is the main contribution, this is the signal from the noise.
Right. Yeah, and so I understand part of the quantum steampunk thrust is optimizing processes. So I guess
Mhm.
that's maybe where is that where the theory ties with the experiment? So, maybe going through multiple iterations to find the best way to optimize a process thermodynamically.
Yeah, that's definitely like an interesting thing. I know one area of research is this so-called like shortcuts to adiabaticity, which basically says like this is a certain class of things you can do on a system that are called adiabatic processes, where roughly speaking, we're just doing things very slowly. So I start with a system and I just fairly, if I have a gas, the classical setup, I have a gas in a box with a piston, and I just very, very slowly open up the piston and I end up with the gas in some final state. But so infinitely slowly is not a real thing. So, but in a lab, you can go slowly where slow is governed by some energy scale. And that's like slow enough and you can really do this. But now the question is, okay, that's one way to get to that final state. But actually, can you get to that final state like much, much faster? Like maybe there's some crazy process where I whip the piston out really fast and then I, throw it in really fast and I do it a couple times. And in the end, the gas is in the same state as if I'd, very slowly opened up the piston. So this interesting idea of like shortcuts to adiabaticity is relevant, in many fields, because like, for example, in like quantum computing, if you're trying to do some sort of simulation, current machines are very limited by their runtime and the coherence times, the T1, T2 times of their qubits. So the faster you can do some sort of computation, the better. So if you can understand how to do some sort of adiabatic unitary with some other much faster unitary with fewer gates, like in a lab setting, if you want to prepare some state, and you say the way I do it is I start with my preparation, some device, and then I have to do this adiabatic process that's very slow, you might very well be interested in a shortcut to this adiabaticity.
And so you mentioned their pistons, and earlier you mentioned quantum engines. I guess when I think of quantum engine, maybe as you've described the process of or energy transfer, I should say, is this the idea of producing work at a very microscopic level through heat differences or through energy differences?
Yeah, yeah, and I think definitely the piston analogy is not so useful when we're thinking about quantum systems. But I think for that, really going back to what we were talking about earlier, and you were mentioning like the quanta of energy levels. So we just think about like an atom with like two energy levels, like a low and a high one. Then you can think about your engine as just kind of operating between that. So there's some electron in a low energy level, it gets kicked up to a higher energy level, and then maybe it spends some time there, and then it's kicked down, and so kind of just extracting energy from these like hops between energy levels. And in terms of like storing it, generally like a lot of these papers, the setup is to say my sort of work reservoir. So the thing in like my sort of battery, which I'm charging up, storing, is just like these, it's like a ladder. It's like these equally spaced energy levels. And at the beginning, it starts off with a whole bunch of, say, electrons in the bottom level. And over time, you run your engine and you like move this electron up the rungs of the ladder. And in principle, then, you disconnect this battery. There's an electron sitting up that high level, and you could connect it to something else, and the electron would, hop down these energy levels, and that's useful work that you could put into your next system. So that's kind of like I think the way to think about, generally like the sort of picture for quantum systems that's like the most intuitive and the most common, whereas like for classical systems, I think it's like piston.
Yeah, that's a really good picture, actually. Thank you for that. Yeah, I think that really helps. And so you've really described a whole lot of really fascinating concepts. And just before we end, I just wanted to say, in terms of, the area that you're working in, quantum steampunk and quantum thermodynamics, and in terms of what we could expect to see in the future, like what's the most exciting upcoming thing for you, or the most exciting potential for you out of all of this?
That's a great question. I think one thing that I've been thinking a lot about sort of recently is how
Our
quasi-probabilities
thanks go to
can be
today's
used in
guest
quantum
and to you for
thermodynamics.
listening to the Quantum Feedback
So,
Loop.
we're used to
Please subscribe to
probabilities.
this
It's like
podcast wherever you get your
probability
podcasts.
distribution. It's like a number
And
of,
don't
like
forget to
chances
check
of
out the
different
Quantum
events.
Record
So it's
at
always like a positive number.
thequantumrecord.com.
And these
The
numbers all
Quantum
add up to
Record is a
one
monthly
because
journal of
something of these
philosophy,
happened.
science,
So we know
technology,
what
and time,
probabilities are.
where you'll find the latest
But it turns
developments in
out,
our rapidly
quantum
evolving
theory
technological
can't
world.
be just described with probabilities and sort of various precise ways to formulate that. But one way we can go beyond probabilities is to talk about quasi-probabilities. And here we say, well, it's like a probability in that we have a bunch of numbers that add up to one, but maybe there's some other things that they don't obey. So for example, some of the numbers could be negative. And of course, like a negative probability makes no sense. And so this lacks the same interpretation as usual probabilities. But in return, they let us kind of satisfy some other axioms which probabilities can't, and they're kind of very useful in their own right. So this is something we looked at in our project on entropy production. But I think it's something where, there are some results behind how quasi-probabilities can be used to sort of model mathematically some things in quantum thermodynamics. But what I think would be really interesting is finding sort of a physical connection to say that, okay, this is a quasi-probability. It's kind of this mathematical object we use to understand some of the physics. But we also know that we can measure this quasi-probability in a lab in principle. And so how do we kind of connect that? Like, what is this quasi-probability really telling us about what's going on? Is there sort of a way to use them and understand a picture with quasi-probabilities beyond just like a mathematical tool, but really as kind of a nice picture of the underlying physics?
I'm trying to think actually. So as you describe quasi-probabilities, I'm thinking it's not necessarily looking at the probability itself, but the relationships between probabilities. Do I have that?
Yeah, that's actually a great way to put
Yeah.
it. Yeah, like on its own, it's not really a probability. It's
Right.
almost like a difference of probabilities or a sum of
Right.
probabilities, and it's
Right.
kind of yeah, that's a really nice way to put it.
That's fascinating. Yeah. Yeah. Really interesting. So yeah, we'll be very interested in seeing what comes out of your work and Nicole's work. And I really think it's a fascinating area of study that we'll definitely want to follow. So I really want to thank you for your time in this. I learned so much, and I think our listeners will be very intrigued to think about where this can go. So I wanted to thank you for your time, and we hope that we can follow up with you at some point in the near future.
Yeah, no, thank you, James. Absolute pleasure. Really, really great to talk about these ideas with you and some really fantastic questions.
Well, thank you. Thank you very much, and we'll talk soon.
Great. Thank you
Thanks.
so much, James.
Bye. Our thanks go to today's guest and to you for listening to the Quantum Feedback Loop. Please subscribe to this podcast wherever you get your podcasts, And don't forget to check out the Quantum Record at thequantumrecord.com. The Quantum Record is a monthly journal of philosophy, science, technology, and time, where you'll find the latest developments in our rapidly evolving technological world.